Hello and welcome to lecture 3 of the course on quantum entanglement and non-local games. Today we will be looking at a new game which is called the Magic Square game. Until now we have already seen the CHSH game wherein the classical players could not get a probability of success more than 3/4, whereas the quantum players were able to achieve a probability of success of roughly 0.85. Now we are going to look at a game where the classical players, their probability will be upper bounded by a value that will be something like 17/18, but the quantum players will win with probability 1. Right, so this is even more interesting now because quantum players are somehow able to win the game deterministically, whereas the classical players are not. So let's get to the description of this game. So here, as before, we still have two players and we can still call them Alice and Bob. And in order to understand this game, we consider a grid of 9 variables, a 3x3 grid of 9 variables. So let me call these variables as V1, V2, V3, V4, V5, V6, V7, V8, V9. And then on 9 variables, we have some constraints. So what are these constraints? So first constraint is that the sum of the variables across the first row, that is V1 plus V2 plus V3, this must equal 0 modulo 2. So consider each of them as binary variables. And modulo 2, the first row should sum to 0. Similarly, the second row should also sum to 0 modulo 2. The third row should also sum to 0 modulo 2. And then we have that the first column sums to 0 modulo 2 again. The second column sums to 0 modulo 2. And now here's something different. The third column sums to 1 modulo 2. So I can actually label these constraints as R1, which means the first row, R2, R3, then C1, C2 and C3. So each of the Ri's are that some of the variables in the given row, they sum to 0 modulo 2. Each of the Ci's are such that the sum of the variables is 0 modulo 2 except for the third column where it is 1 modulo 2. Okay. So let me actually just write these constraints down as well. So what I have is that V1 plus V2 plus V3 is going to 0 mod 2, R1, V4 plus V5 plus V6 is going to 0 mod 2. I call this R2, V7 plus V8 plus V9 is going to 0 mod 2, R3, and then I have the corresponding column constraints, which is V1 plus V4 plus V7 is 0 mod 2, V2 plus V5 plus V8 is 0 mod 2, and V3 plus V6 plus V9 is 1 mod 2. C1, C2, C3. So the first question which comes up is that is it possible to satisfy all these constraints? So the answer is no, because if you sum up the left hand sides of each of these constraints, you are going to get 0 modulo 2. Why? Because every variable occurs in exactly one row and it occurs in exactly one column. So if I sum over the left hand side of each equation, every variable will occur twice and the sum is going to be 0 mod 2. Whereas on the right hand side we have 5 zeros and we have a single 1, so this is congruent to 1 mod 2. So if all of these constraints are true, then we'll get something like 0 is congruent to 1 modulo 2, which is wrong. So it's of course not possible to satisfy all these constraints. So the game which we design is as follows, that firstly we have these set of constraints, which is, so I have defined my set S to be the set of constraints R1, R2, R3, C1, C2, C3. And I define my set T, which is the set of Bob's inputs. So S is the set of Alice's inputs, T is the set of Bob's inputs. So the set T will consist of the binary variables, so variable index essentially. So V1, V2, V3 up to V7, V8, V9. So these are basically just the index of the variable is given as input, not the value of the variable. And now what Alice needs to output is that, so this is Alice's input and this is Bob's input set. Okay, this is an input set. Okay, now Alice needs to output 3 bits and Bob needs to output a single bit. So here Alice will be given a constraint as input and needs to give an assignment of the 3 variables in that constraint. The Bob is given a single variable as an input and he needs to give a value assignment to that single variable. And the inputs are such, these S and T, they are designed in such a manner that so when Alice is given a constraint, Bob is given a variable from the same constraint. And Alice is given a constraint uniformly at random from the set of 6 constraints, and Bob is given one of the variables from the same constraint uniformly at random amongst the 3 variables in that constraint. Okay, so here our distribution over the inputs pi st is going to be 1 by 18 for all constraint comma variable such that variable belongs to the constraint. And so you can check that there are 6 possible constraints. Each of these has 3 possible variables. So there are 18 possible inputs, and we are giving a uniform probability of 1 over 18 over each of these possible inputs. So this is how we have defined the set pi st. Okay, and let's also take an example. So let's say that suppose I give Alice as input the first constraint, let's say R1. So I have Alice, and let's say the input is going to be say R1, and let me say I give Bob as input the second variable, which is V2. So V2 lies in R1, right? So this is a valid set of input. And now here Alice needs to give an assignment of V1, V2, V3. Suppose Alice outputs say V1 equals 0, V2 equals 0, V3 equals 0, and let's say Bob outputs V2 equals 0, then they'll win the game, right? So here the winning condition so firstly, Alice's output must satisfy given constraint. Secondly, Bob's output must be consistent with Alice on same variable. Okay, so here for example, Alice was given as input V2, and so Alice was given as input R1. She outputted V1, V2, V3 as being all 0, and Bob outputted V2 being 0. Since these two are consistent and Alice's value assignment satisfies the given constraint, we see that both the conditions are met and they indeed win the game. Suppose if Bob would have outputted say V2 equals 1, then they'll lose the game because these outputs are not consistent with each other, because Alice is saying V2 equals 0 and Bob is saying V2 equals 1. On the other hand, if let's say Bob gives an output V2 equals 1 and Alice gives an output V1 equals 0, V2 equals 0, V2 equals 1, V3 equals 0, then we'll see that the outputs are consistent but the constraint is not satisfied, so they'll again lose the game. So both these conditions should be met. Okay, and what our claim is that a deterministic classical player let's say a pair of deterministic classical players can win with probability at max 17 by 18. So there is one classical strategy which can win with probability 17 by 18, which is as follows: that I consider an assignment of these variables as being all zeros. Okay, and now what Alice is going to do is that given a row or a column, she'll just say that all these variables are 0, and Bob, when given an input, will also say that the given variable is 0. So here they'll always be consistent. But now Alice is going to satisfy at max 5 of the constraints, right? Okay, so this does not work. This doesn't work. A strategy that works is as follows. So let's write down the strategy. So Alice given R1, R2, R3, C1, C2 outputs all zeros. Okay, given C3, she outputs 0, 0, 1, and where so this is for the third column. For third column we have the variables V3, V6, V9. So V3, V6, V9. Okay, and what Bob is going to do is that Bob will output a 0 each time. Okay, so note that V9 also occurs in the constraint R3. In this case, Alice is still giving as an output 0, 0, 0, but when given C3, she outputs 0, 0, 1 to the 3 variables. Now, okay, so let's say in what cases they win and in what cases they lose. So firstly, see that we have assigned Alice's outputs in such a way that Alice will always satisfy the constraint. So that is not an issue. So constraint satisfaction is always met. The issue comes up whether the variables are consistent or not. And we see that when Alice is given the constraint C3, then Bob's output for V9 will be inconsistent because Bob will output a 0 over there. For each of the other constraints, Alice's outcomes are going to be all 0 and Bob's will also be all 0, and the values will be consistent. So they'll win the game in every case except for C3, V9, right? Even with C3, with the other variable assignments, they'll win, but for the assignment of C3 and V9, when Alice is given as input C3 and Bob is given V9, then they are going to lose the game. Okay, and so this occurs with probability 1 over 18, so winning probability is 17 by 18 here. A question that comes up is that, well, why is it the best? Why can't we do better? Because the answer is that since there is no consistent way to assign the variables, there is no way to win the strategy. The reason being that Bob never knows which of the constraint Alice is being assigned, and hence Bob has to output the variables in a way which is independent of the constraint which Alice has given. And in this case, since we see that there is a clash for R3 and C3, right? So in R3 we want that V9 is 0, and in C3 we want that it is 1. So you can check that, right? So just try working out and you'll see that you won't be able to assign, you won't be able to create a strategy which will win in every case, right? Because if they win in every other case except C3 V9, then they are going to lose in the case for C3 V9. So this is also something I am leaving as a homework exercise. Now coming to quantum. So what I claim is that the quantum players can win with probability 1, right? So they can win deterministically, and this is the interesting part. So how can they do that? So we'll now design that strategy. So the strategy is as follows: that Alice and Bob share a maximally entangled state in dimension equals 4. So what this happens to be? This happens to be sum over k from 0 to 3 get kk over square root of 4, right? So half of sum over k from 0 to 3 get k comma k. And this is actually equivalent to sharing 2 bell pairs. Which is 1 over root 2 0 0 plus 1 over root 2 1 1, the first qubit of Alice and Bob, tensored with 1 over root 2 0 0 plus 1 over root 2 1 1, the second qubits of Alice and Bob. So diagrammatically it's something like this, that there is the first EPR pair, they are sharing, and there is a second EPR pair. So they hold 1 qubit each of the 2 EPR pairs, and given the inputs, they use the following operators to make their measurements. So what Alice is going to do is that, so let me write down Alice's operators. What are these? So we'll draw these operators on a grid. So for each of the variables, she'll need to measure an operator on her share of qubits. Since she has 2 qubits now, these operators are in tensor products of these poly gates, which are single qubit gates. Okay, so suppose if Alice is given the first row, she needs to measure the variables v1, v2, v3. What she'll do is that she'll measure these operators, and each of these operators will give her outcomes in plus minus 1, and here we'll map minus 1 to 1 and 1 to 0. Okay, and okay, because these are actually essentially binary variables, so they are going to give us output minus 1 plus 1, and we'll always associate 1 with 0 and minus 1 with 1. Okay, so here suppose if I call this outcome as say, so let me just call this as v, and let me just call it v prime, then v prime is going to be minus 1 to the power v. Okay, so this is just a binary mapping which we are maintaining, and see, actually the thing is that over here we have XOR and over here we have product. So product corresponds to XOR here when we do this sort of a mapping. Okay, and so given the first row, she'll make the measurements associated with the operators in the first row and give their corresponding outputs. Given the first column, she'll make the measurements associated with the operators in the first column, and so on. Okay, what Bob is going to do? Bob will also use the same sort of matrix, and Bob measures the transpose of the variable assigned. Okay, so if Bob is given the input v1, then Bob will measure in the operator I tensor z transpose, which is I transpose tensor z transpose, which is also I tensor z, and so on. Okay, now why is this strategy correct? So there are 3 things which we'll need to verify. So firstly we need to verify that operators in row and column, they commute. Only then can Alice make consistent measurements across the set of operators in a row and column. So is it true? Let's see. So if I look at the first row, then I tensor Z, Z tensor I, Z tensor Z. So since all these are Z variables, they'll always commute. Similarly for the second row. For the third row, here I have a mixture of X and Z's. So X and Z anti-commute, Z and X also anti-commute, but together, when I'll take the products of their tensor products, they'll actually commute, because whenever Z and X, they go across each other, they'll produce a minus sign, but then I'll get a minus sign twice. So the details I leave you to verify. Similarly for ZX and YY also. And similarly for first column, I have only X's on the first part and Z's on the second part. For the second column, again I have Z's on the first part, X on the second part. And for the third column, I always have two non-commuting polys, but then there are two of them, so they'll cancel their minus signs. So this is something which you need to verify. So this is also a homework. Okay, and yeah, so keep writing the solutions to homework in the comments. Second thing we need to verify is that the row and column, they have the correct product. Okay, so what does that mean? So if I multiply the operators of the first row, I'm going to get I tensor Z times Z tensor I times Z tensor Z, and that will be like Z square tensor Z square, which is going to be identity cross identity, which will be identity. So the product over here is going to be identity. The product of the second one is also going to be identity. The product of the third one will have XZ, and Y is also iota XZ. So that will give me like iota times xz squared, and this will be tensored with iota times zx times xz, and so you have to verify that this product is going to be identity again. Okay, because they'll be so when I'll do this thing, zx squared, I'm going to get minus identity, but then there'll be an I square also, so that will cancel off. So again, you have to verify. Also verify that the product of operators along the first column is also identity. There's an x square tensor z square. So you need to multiply the operators across each column. And now for the second one, you will also see that this is identity. So when I'm writing the product is identity, it actually means identity cross identity, right? Or you can write it as identity on 4 dimensions. So for the second one, for the last one, however, I see that this is zxy, tensored zxy, and so that will actually turn out to be minus identity. So all these 6 equations you'll need to verify. But how does that help us? That helps us because now each of these operators, when measured, they give a plus minus 1 valued outcome. If the product is identity or minus identity, that means that the products of these plus minus 1 valued outcomes, they will be deterministically either plus 1 or minus 1, depending on whether the product of these operators is either plus identity or minus identity. Because plus identity overall, it always measures to 1, and minus identity always measures to minus 1. This is irrespective of even the state. Okay, and if they satisfy these relations, which means that in the XOR domain, the ones which are producting to 1, they'll correspond to summing to 0, and the ones which product to minus 1, they'll correspond to summing the 0, 1 variables to 1. So which means that this will also be, as in the constraints will all be satisfied. And thirdly, what we need to show is that Alice and Bob have consistent outcomes. So how do we show this now? In order to show that the outcomes are consistent, what we'll show is that the product of the outcomes is always 1. In the minus 1 plus 1 regime, if the product is 1, and that will mean that they are equal. So how do we show the product of outcomes across Alice and Bob? So let's say that suppose Alice is measuring the variable O and Bob measures O transpose, right? Because this is how we define the strategy, that Bob measures the same variable in the same operator, this operator grid we drew, and however in the transposed regime. And now this is going to be psi with O times O tensored I psi. Right, so we are using the lemma which we derived in the first lecture. So this is psi O square tensored I psi, and O square is nothing but identity, because these are all binary variables. So psi identity cross identity psi, which will happen to be 1. So which means that the product of their outcomes are going to be 1, and hence their outcomes are going to be consistent. So we have shown that quantum strategy gives outcomes which are consistent and they satisfy all constraints as well. So these are both the sufficient conditions to win the game, and they win the game deterministically. Yeah, whereas the classical players were not able to win with probability more than 17/18. So this is quite an interesting example, because the difference is now quite big, right? So earlier it was just a higher success probability, now it's winning deterministically. Okay, thanks. Yeah, that's it for this lecture. The next lecture we'll look at the generalized notion of XOR games.